All right, in this example using voltaic cells, we're going to take a look at a cell that's already been pre-built for us. So we have lead nitrate with lead as an electrode and magnesium nitrate with magnesium as an electrode. We have a salt bridge, which generally speaking is normally going to have KNO3 in it, 9 times out of 10. And we also have our piece of wire attaching our two electrodes so that a circuit can be completed. Here's how this is going to be different than our first voltaic cell reaction. In the first voltaic cell reaction, if you remember back to it, we went through and we already knew what our oxidation reaction was and our reduction reaction was based on our total reaction that was given. In this particular example, we're going to try and figure out what the oxidation and reduction reactions are. And so let's take a look at our two possibilities. We have a possibility of our lead and our magnesium. And so to figure out which one is going to be oxidized and which one is going to be reduced, and to write the correct reactions underneath, we need to look at a cell potential chart, so a reduction potential chart. So I'm interested in looking at lead and magnesium. Okay, so we're going to go to the cell potential chart. And if you look here, I have both the magnesium and the lead circled already and highlighted. This is reduction potential. If you look at each of these reactions that are written, most of the time our cell potentials are going to be given as reductions, which is what these are. And if you look at the two values, we've got negative 0.126 for lead and negative 2.340 for magnesium. And the more positive is going to be the one that is going to be favorable as far as reduction. And so the more positive of the two is actually the lead. So the lead is going to be reduced, and that means that the magnesium is going to be oxidized. And just a quick reminder, when we write that oxidation, it means that that's standard electrode potential, the EMF is going to be flipped as far as the sign is concerned because we're flipping the reaction. So again, we know that the lead is reduced and then the magnesium is going to be oxidized. And how do we know that? We look at the values in the chart. The one that's the more positive is going to be the one that's going to be reduced because it's written as a reduction potential. All right, so back to our example. We know that lead is going to be reduced, and I like writing that right away, and that the magnesium is going to be oxidized. Now we're going to write out those reactions, which I found over the years that kids struggle with the most. Just a quick reminder, Leo the lion goes grr, so loss of electrons is oxidation, gain of electrons is reduction, or you could think of this as oil rig. Oxidation is lost, reduction is gain. So let's look at these. If this is going to be reduced, the lead is going to be reduced. It means it needs to be reduced in charge. So it starts as something that's more positive. So since it's being reduced, it starts as Pb2 plus and ends as Pb. Since magnesium is going to be oxidized, it's going to lose electrons, or oxidation is lost, it's going to lose electrons, we're actually going to become more positive. So it starts as magnesium and it's going to become magnesium 2 plus. We're going to go ahead and add our electrons in there in order to balance it out. Plus 2 electrons here, plus 2 electrons here. And then we're going to label these with anode and cathode. So quick reminder about that. The anode is going to be with the oxidized side. So this is our anode. And then reduction is going to be with our cathode side. So again, the way I was able to figure out which one was oxidized, which one was reduced, was I looked at a cell potential chart and I looked up the electrode potential for each. Again, because cell potential charts are almost always written as reduction potentials, the most positive reduction potential is going to be the species that's going to be reduced. The other one is going to be oxidized. So again, I figured that out from this cell potential chart. So now that I know that, let's go ahead and add a couple of quick things onto my voltaic cell. Let's start by talking about which way the electrons are going to flow. So remember, electrons are always going to flow from where they're produced to where they're used. So from anode to cathode. So in this case, my electron flow is going to be right to left. So I'm just going to write down electron flow. And now let's talk a little bit about what's happening at each of the electrodes. So over here, I am taking my magnesium that is a solid as an electrode, and I am forming more magnesium 2 plus ions. So remember, there's already some magnesium 2 plus ions in solution along with our nitrates. But because of the reaction that's happening here, I am actually forming more magnesium in this solution as a 2 plus form. Over on the left-hand side with the lead, again, I'm taking lead that's in solution and turning it into the lead that's the electrode. So I may have started with lead in the solution. So let me just draw some leads. Again, I may not be completely stoichiometrically accurate here, just bear with me. But I'm taking some of that lead that's in solution and turning it into lead that is the elemental form. So I'm actually reducing the amount of positive ions in the solution. And the reason that's important is it's going to tell us how the ions in the salt bridge move. Remember, ions in the salt bridge are all meant to keep the solutions electrically neutral. Okay, they're meant to flow to keep these solutions, the solution here and over here, electrically neutral. So because on the right-hand side, I'm forming additional magnesium 2 plus, I need to have more negatively charged ions flowing into that solution. So the way the salt bridge is going to look is that nitrate ions, negative nitrate ions, are going to flow into this solution. On the left-hand side, because I am reducing the amount of positive charge in the solution, again, if you remember, I crossed them out, I need that to be replenished in order to keep that solution electrically neutral. So the potassium ions are going to flow into this solution. Last but not least, let's talk a little bit about what our cell value is, our E cell for this. Let's go ahead and take back a look at our cell potential chart. We have our lead, which was negative 0.126. So lead was negative 0.126. And then we have, that's from our lead. And then we're going to take a look back at our magnesium, which was negative 2.340. Now, quick reminder, since this was flipped, we aren't reducing, we're oxidizing. We have to change the sign. And so instead of being negative 2.340, we're going to change it to positive 2.340. So again, we take our reduction potential and we keep it the same, negative 0.126. We take our oxidation potential and we flip the sign. And we add those two together in order to get our final answer. And so when I do that, I'm going to take my negative 0.26 and add it to my 2.340. I'm doing that calculation right now. I get 2.214 as my E cell, and that's in volts. And that would be what you would read if you were to put some sort of a sensor right here. That's what that would read as far as the electron flow. All right, that is all for the second type of Voltaic cell example. Again, in this example, we were able to figure out what was oxidized and reduced by using a cell potential chart. And then we were able to label our diagram appropriately, figure out the E cell, and answer some questions about it as well.